Consider a container as shown, which is filled with a liquid of density rho, and assume the liquid is filled up to a height h, or okay, let's call it capital H. From the base, and assume cross-sectional area of the base or the upper surface. Okay, assume its cross-sectional area is capital A. Okay, so if you know capital A and height, you know the total volume of liquid inside the container, and based on density, you can even tell the total volume, total mass of the liquid inside the container. Fine. Now let's say this container is accelerated downward with an acceleration of A, small a. Now we know how pressure varies with depth in such cases. Okay, we derived this in the last class. Pressure at a depth y will be P naught, pressure at the free surface, plus rho g minus a multiplied with y. Okay, effective gravity will be g minus a when the container is accelerated vertically downward. Fine. Now, as long as a is less than g, this equation is fine. You can easily tell what is the pressure anywhere in the liquid, at any depth in the liquid. Then last class itself, we even discussed this case where acceleration is equal to g. If a is equal to g, then the pressure at any depth y will be p naught plus 0. That is p naught itself. That means if acceleration of the container is equal to acceleration due to gravity, what does that mean? If the container is in free fall, okay, pressure will be uniform in the liquid. The entire liquid will be under the same pressure. Next, what if the acceleration of the container, downward acceleration of the container is greater than acceleration due to gravity? Okay, we had briefly talked about this also. If there is a plane, or if there is a box like this, right, or an open container like this, you can think of this as an elevator also. And on the floor of the elevator, let's say there is a block. It is not rigidly attached to the floor of the elevator, right? Now, if the elevator goes down with an acceleration greater than g, then what will happen? The block goes down basically due to gravity. There are no other downward forces acting on it. Okay. So what you will observe is that the elevator will accelerate faster than the block. Somehow, by some means, the elevator is going or accelerating faster than gravity, but the block cannot accelerate that fast. Okay, block can only accelerate at a maximum rate of g in the downward direction, not more than that. So this is what will happen. You will see the block rising up relative to the elevator. Actually, it is falling down. Relative to elevator, it will appear to rise up. Okay. Now, on a block also, even on solid objects, there is atmospheric pressure acting. So due to atmospheric pressure, there will be a force from above, which is atmospheric pressure multiplied with the area of that upper surface. But there will be a force from below also. See, below it also there is air. Air molecules will be striking it. Fine. And if air molecules are striking it, they'll be exerting a pressure on it, due to which there will be a force exerted on it, P naught into A. Pressure is same everywhere in air. Okay. I mean, for small heights, there won't be significant change in pressure in air. Air is a gas. Okay. In liquids, based on depth, the pressure will significantly vary. But in a gas, for small depths or small heights, there won't be significant variation in pressure. So upper surface of the block will be at pressure P naught, experiencing a force P naught into A. Lower surface of the block will also be at a pressure P naught, experiencing a force P naught into A. Those forces will balance. The only net force acting on the block is its weight, mg, which makes it go down with an acceleration equal to g. So a block placed on the floor of an elevator cannot go down with an acceleration greater than g without the help of some other forces. Okay. Now, if you try to do the same with the liquid inside a container like this, suppose the container goes down with an acceleration greater than g, then the liquid in the container will have a tendency to rise up. Okay. But see, there are other forces, other significant other forces acting on the liquid. Suppose this container tries to go down with an acceleration more than g, on the liquid, there are additional forces as well. Due to atmospheric pressure, there is a force from above, which is P naught into the cross-sectional area of the upper surface, which we considered as A, right? And along with that, the liquid's own weight will also be pulling it down, mg, or density into volume into g. For convenience, I'm writing it as mg. From below, there won't be force due to atmospheric pressure, because between the lower surface of the liquid and the container, there is no air present. So on a liquid, that P naught into A will not be considered from below. On blocks, you will have to consider, actually, you don't even have to talk about it. See, even if a block is perfectly in contact, I mean, okay, maybe I should not use the term perfect contact. Even if a block is placed on the floor, there will still be some holes for air to enter between the block and the ground. Okay, two solid surfaces will never perfectly be in contact that they won't even allow air to enter between them. Fine. If you do that, of course, okay, again, I think I gave a loose statement. In some cases, yes, solid surfaces can be perfectly in contact. Have any of you uh, seen or used the suction cups, or those suction holders will be that, no? Just a moment, I'll show the picture, you'll understand better. These things. Uh, some of you may have seen them being used for attaching car window shades. Uh, some of them, I mean, some of you may have seen them in like household furniture or accessories. Basically, if there is a smooth surface like glass, okay, like a glass surface, you just press this suction holder against the glass surface, it will kind of stick to it. It won't act, there's no gum actually, but it will appear as if it has stuck to the surface. Okay, I'll show you another picture also. Yeah. So basically here what they did, that toothbrush holder that is there, they have attached it to the tile, okay, using a suction holder. So basically what happens in that suction holder is, suppose this is the surface on which you want to stick it. Okay, it can be stuck to a horizontal surface also, no problem. Or okay, let me consider a vertical surface itself. Do any of you have any idea how it works? How does it kind of stick to the surface? They can be removed also.
So
Yeah,
it
go ahead.
traps the air. Like it traps the air inside, and there's like air, less air pressure inside, and outside there's more air pressure.
Ha. Okay, you should not say it traps the air inside, but yeah, I mean, whatever you said about pressure is correct. So basically, imagine a suction cup like this or a suction holder like this, right? Usually they are made of rubber or silicon, flexible material, not perfectly solid. I mean, not perfectly rigid. Okay. So when it is open to the atmosphere, the pressure outside is P naught, atmospheric pressure. The pressure inside this cone, okay, that suction holder that is there, the pressure inside is also P naught itself. Air is there everywhere. Okay. Then what you do when you look at it from the side, okay, or the smooth surface, and you press the suction holder against the wall. When you press the suction holder against the wall, basically or effectively what you will be doing is you will be making air inside escape. Okay, there'll be small gaps here. Like when you press it against the wall, gaps will get created automatically and the air escapes. Okay, you press it completely against the wall, all the air will escape. Okay, so situation becomes like this. It will become almost flat. Okay, you can see that in this picture. When it is pressed against the wall completely, it becomes flat, almost flat. So there is almost no air now between the rubber and the tile. Okay, let's assume it is being pressed against a tile. Okay, so there's almost no air between the rubber and the tile, rubber, silicone, whatever it is. So if there is very less air, that means there is very less pressure. So the pressure here is almost equal to zero. Let's say we are effectively creating a vacuum there. Okay, so approximately zero pressure. Okay, but outside there is atmospheric pressure. So now if you consider that flattened holder, suction holder that is there, Just a moment, let me copy it. Yeah, if you consider this, the pressure on the left side where it is pressed against the tile, this pressure is approximately equal to 0. The pressure on the right side is atmospheric pressure P naught. So basically, from outside, due to atmospheric pressure, there will be significant force acting on it. Atmospheric pressure is a huge amount of pressure, I told you. Okay. Now see the suction holder, how much could its area be? Let's say 3 centimeters by 3 centimeters. So 9 centimeters square. For convenience, let's assume 10 centimeters square. Okay. So that suction holder, once it is pressed against the centimeter square, centimeter is 10 power minus 2 meters square, 10 power minus 4. So effectively it is 10 power minus 3 meters square. Okay. Now we know atmospheric pressure is a huge amount of pressure, approximately 10 power 5 pascals. Now if that pressure is multiplied with this area, then the force with which it is being pressed against the wall, okay, basically the resultant of these forces. Once the suction holder is pressed flat, all these forces will be almost in the same direction, right? Perpendicular to the wall. So I'm assuming they are all in the same direction. If they are all in the same direction, force can be simply expressed as pressure multiplied with area. Pressure is 10 power 5 pascals. Area is 10 power 100 newtons. 100 newtons is like the weight of a 10 kg object. That's quite significant. Okay. So once you press the suction holder against a smooth surface, ensuring no air enters, then you will effectively be pressing it against the wall, or the atmosphere will be effectively pressing it against the wall or the tile with a force of 100 newtons. That is why the suction holder does not come out. Okay. If you can somehow exert a force greater than this, then it will come out automatically. I mean, not automatically. You will be able to force it out also. Okay. You can pull them out. Right. Why are we discussing all this? Just to show you that on solids also, effect of atmospheric pressure can be significant in some cases if you ensure that air does not enter on one side. Okay. Now between rubber and glass, it is possible. Glass surface or tile surface is quite smooth. Then you can prevent air from entering. Okay. Then force due to atmospheric pressure will be only from one side, and that will be a significant force. But usually when a block is placed on the ground or the floor of an elevator, those are not very smooth surfaces. Okay. So like we never talked about this when we talked about forces and all, but it is indirectly assumed that below the block also, between the block and the ground also, the pressure is atmospheric pressure. Okay. And above also it is atmospheric pressure. So the effect of atmospheric pressure can be ignored. That force will be there from both sides. Okay. Now, if a liquid is present in a container like this, liquid will spread on the surface of the container thoroughly. It won't allow air to enter. Okay. And on the sides also, there is no gap for air to actually enter and go to the lower side of the liquid. So force due to atmospheric pressure will only be from above. Therefore, the total downward force on the liquid in this container, how much will it be? Force due to atmospheric pressure from above into gravity. Okay, we took area of cross section as A and height as H. This is the total downward force on the liquid. Fine. Now, suppose the suppose the container goes down with an acceleration equal to g. Okay, we kind of already discussed this case. If container goes down with an acceleration equal to g, pressure will be uniform throughout. Okay. Let's consider the case where acceleration is greater than g. The total downward force acting on the liquid is this much. Fine. And there will be some upward force also acting as long as the liquid presses the base of the container. If the liquid is pressing the base will push the liquid in the upward direction. That normal force will be there on the liquid. Okay. That also we have to write in terms of pressure only actually. So, okay, wait, let's first consider the case where liquid is going down with an acceleration A itself. So downward acceleration G itself. Let's say downward acceleration is G. Then what will happen? See, the total downward force on the liquid is this much. That means the downward acceleration that it can go with is mass multiplied with downward acceleration, and that's the maximum downward acceleration. If there are no upward forces, if these downward forces are only acting, then the maximum acceleration with which it can go down is rho AH gets cancelled. You get G plus A and A will get cancelled. P naught by rho H. it can go with this much acceleration, up to this much acceleration. Okay, because gravity is not the only thing pulling it down. Suppose the container goes only with an acceleration equal to g. G is less than the maximum acceleration the liquid can take. Liquid can attain up to this much acceleration. G is definitely less than that. Okay. So what will happen? The liquid has a tendency to move faster. The container is not moving that fast. So some pressing will still be happening. Okay. So some upward force will still be acting on the liquid on the base. So some pressure will still be on the base, and that pressure is P naught itself. We know that if acceleration is equal to G, then the pressure at any depth is P naught. So the pressure here also will be P naught, and with that pressure, the liquid will be pressing the container. The container also will be pushing the liquid in the upward direction. Okay. So P naught A from above and P naught A from below will be acting. So those two will cancel. Under the influence of mg, the liquid also will go down with an acceleration equal to g. Now suppose the acceleration of the container is more than g, but not this much. This is the maximum acceleration with which the liquid can go down. Okay. So let's consider that case where the downward acceleration of the container is greater than g, but less than this maximum downward acceleration of the liquid. Okay. Then what will happen? See, when acceleration is equal to g, the pressure at any point of the base, not just the base, when acceleration is equal to g, pressure everywhere was P naught. Okay. So on the base also it was P naught. So the into A and this cancelled. The effective gravity became G. Now what will happen? If acceleration is more than G, then the pressure at a depth Y will be P naught, right? A is more than G. So this part becomes negative. What does that mean? That means the pressure will be less than P naught at a depth. Okay. So if the container goes down with an acceleration greater than g, the pressure actually decreases with depth. Okay. Why? Because pseudo force will be acting in the upward direction if you take relative to the container, and pseudo force will be more than gravity this time. Because acceleration is more than g, ma will be more than mg. Pseudo force more than gravity, then pressure will increase in the upward direction, or you can say pressure decreases in the downward direction. Then in that case, the pressure on the base will not be equal to P naught. It will be less than P naught. If pressure on the base is less than P naught, okay, at these points, the pressure is less than P naught, then the forces from below will be weaker than P naught A. So now mg will be acting on it, which will give it an acceleration g, and this P naught A minus PA, force from below is PA, P is less than P naught. So P naught A will dominate, PA will be lesser. So there will be an extra force in the downward direction that will give it that extra acceleration. Fine. So if container goes down with an acceleration more than g, the liquid also can take that extra acceleration. Okay, liquid also can go down with an acceleration more than g. But the maximum acceleration with which liquid can go is this much. Okay, if there are no upward forces acting on it, only downward forces mg and that P naught A are acting on it, then it can go with that much acceleration, the expression we have written on the right side. So container also can afford to go with an acceleration, with a downward acceleration. If this happens, then the pressure at a depth y will be P naught plus rho g minus a. If you do g minus a, it will become minus P naught by rho h into y. Okay. Basically, this is g minus a that I have written here. And if y is equal to h, means at the lowest point of the liquid, the pressure will become absolutely zero. What does pressure becoming zero? The liquid is now not pressing the base at all. It is about to lose contact. Okay. So if the container goes with this much acceleration, which is the maximum acceleration that the liquid can attain, if container also goes with that much, both are going with the maximum possible acceleration. So they are just about to lose contact. If container accelerates any faster than this, the liquid will start rising inside the container. Okay. So if you consider that case now, downward acceleration of the container greater than g plus P naught by rho h. G plus P naught by rho h is the maximum downward acceleration the liquid can afford. If the container goes faster than that, then you will see something like this happening. As I said, the liquid cannot keep up with the container as it goes down. So relatively, you will see it rising up. Now, what happens when it is actually rising up inside the container? It's not pressing the base of the container anymore. So you will see a vacuum here. Vacuum means pressure is 0. That's all. Liquid will be going down due to mg and that atmospheric pressure effect P naught A. So acceleration, downward acceleration of the liquid will be that maximum value G plus P naught by rho H. G plus P naught by rho H. That depends on the external agents which are pulling the container down. Okay. So at the upper surface, the pressure will be P naught. As always, if it is exposed to atmosphere, the pressure is P naught. Lower surface, the pressure will be 0. Fine. So what I want you to understand from all these cases is that first, if container goes down with an acceleration equal to G, then the pressure everywhere will be P naught. On the upper surface will be P naught. On the lower surface of the liquid also, pressure will be P naught. So P naught A from above, P naught A from below will cancel. Liquid also goes down with an acceleration equal to G. If the container goes down with an acceleration more than G, then this pressure will start decreasing. The pressure on the lower surface will start decreasing. But the liquid can still keep up with the container because there is force due to atmospheric pressure from above. So if acceleration of container is exactly equal to G plus P naught by rho H, then what will happen? The pressure at the lower surface will exactly become 0. So upper surface pressure will be P naught. Lower surface pressure becomes 0, or the pressure at the base becomes 0. But the liquid will still be going along with the container with this much acceleration. If container goes faster than that, then liquid will not be able to keep up with it. Okay. Fine. So this is how pressure varies when container is accelerated upward or downward. If container is accelerated upward, it's a straightforward case. Gravity effect will be there. Pseudo force effect also will be there. They'll add up. Okay. Effective gravity is G plus A. So pressure will increase as you go down. It will increase with a higher gradient, you can say. More rapidly it will increase with depth if the acceleration of the container is upward. If the acceleration of container is downward, as long as A is less than G, okay, the pressure will increase as you go down. When A becomes equal to G, the pressure will be same everywhere. When A is greater than G, then the pressure will decrease as you go down. Means upper pressure will be higher, lower surface pressure will be lower. Okay, if acceleration of the container is more than G. And it can go down up to 0. The lower surface pressure can go down to 0 also. Okay.